Hello, in this video we're going to be talking about the truth value or validity of a predicate well-formed formula. I mean the formula which has for all that exist. How do we know it's valid or not? So in the last section, the truth value of propositional well-formed formula depends on the truth value assigned to the statement letter. So that the truth value of predicate well-formed formula depends on interpretation. For example, if I say for all x, p of x implies q of x, it depends where is x. But when you have propositional logic, for example, a implies b implies c, you could do a truth table and see if it is valid or not. Valid meaning you will have a tautology when at every row. So there are an infinite number of possible interpretations for a predicate well-formed formula and only 2 to the power n possible rows of the truth table for propositional well-formed formula with n statement letter. For here we have A, B, C. That means we need 2 to the power of 3 rows. So it's finite numbers of rows. But for a predicate, it's an infinite number of possibilities. So usually a computer can handle something finite, but not something infinite. So here is where we have propositional well-formed formula. The methodology to find out if it is valid or not, you use the truth table to determine if it is tautology. But predicate well-formed formula, there is no algorithm to determine validity. So we're just going to have to interpret the scenario. Let's see an example. So it says here, decide whether each of the following well-formed formula is valid or invalid. Justify your answer. So number one, for example, we have for all x p of x, this implies that there is some x makes p of x true. And I would say this is valid because if every object in the domain has a certain property, then there exists an object of the domain that has the same property. Because all what we need, there exists one example. Because it's already, we know it's true for all x's, so it must be true for one x. Let's see the second example. For all x, p of x implies p of a. This is valid, obviously, since a is a member of the domain of x. So for all x p of x, I mean for any x p of x is true, well, maybe that x can be a as an example. So this is valid. Next example we have, there exists x p of x implies for all x p of x. Just because it exists for certain x, for certain x p of x is true, it doesn't mean this implies for all x p of x. So obviously this is not valid statement. And I would give an example. It's easy to prove something not valid by just giving a counterexample. And a counterexample would be, if I make p of x odd, there exists some odd integers, then we can say this implies, just because there exists some odd integers, implies for all integers, all integers are odd. So we can say if valid for some objects in the domain, the property does not need to be valid for all objects in the domain. For the next example, we have for all x p of x or q of x. So for any x, either going to be p of x is true or q of x is true, or both of them are true. Does this implies that for all x p of x or for all x is a q of x? And again, I'm going to say this is not valid, and because I could bring a counterexample to show that this is not valid. For example, let's say p of x again is odd, and Q of x is even. So for all integers, so here the domain of interpretation is integers. For all x, either x is odd or x is even. Does this imply that for all integers are odd or all integers are even, which is not true? So it's easy to say that it is false because it's not true for that every integer is even or every integer is odd. And this is how we check if a statement or formula is valid or not valid when you have a predicate logic. And in the next video we'll prove and we'll show predicate logic.